Bienne technology introduces the Orion Mark II, marking a significant advancement in surface analysis. By integrating nuclear instruments and accelerator technology, Orion Mark II enables molecular vision at nanometric scales. This innovation addresses the limitations of current instrumentation in identifying molecular environments just a few nanometers in size. The Orion Mark II provides insights into areas such as semiconductor architecture and molecular-level research in biological systems, offering capabilities previously unavailable in commercial instruments. Its molecular vision opens new possibilities for detecting and identifying individual molecules located within a few nanometers of each other. The Orion Mark II operates as a secondary ion mass spectrometer, NP-SIMS, utilizing nanoprojectiles for surface analysis. Specifically, gold nanoparticles comprising 400 atoms are generated via a liquid metal ion source. These particles, carrying varying electric charges, are separated using a Bienne filter, a device employing crossed electric and magnetic fields to isolate the desired nanoparticles. The primary nanoparticle used is a cluster of 400 gold atoms with a +4 charge, accelerated to hypervelocity speeds of approximately 30 kilometers per second. The system ensures precision in lateral resolution by selecting a single nanoparticle from the beam, which is directed through an aperture and impacting the target, enabling detection of molecules and atoms adjacent to and within a few nanometers of each other. Upon impact with the sample, the hypervelocity gold nanoparticle causes the ejection of material, resulting in a crater between 10 and 15 nanometers in diameter and up to 10 nanometers deep. This crater determines the lateral resolution of NP-SIMS. A portion of the ejected particles is ionized and subsequently identified using a mass spectrometer. Typically, dozens of secondary ions specific to molecules of interest are released with each nanoparticle impact. These ions are accelerated and analyzed via a time-of-flight mass spectrometer equipped with a reflectron to enhance mass resolution. Each impact produces a distinct mass spectrum. The secondary ions observed are recorded and the process repeats, typically at 1 kHz, which yields around 1 million spectra in about 20 minutes. One application involves understanding how organic LEDs assemble on a surface. The orientation of these bottle brush molecules in OLED displays can adversely impact the screen resolution. Ideally, the molecular bottle brushes should stand up as vertically oriented rods with a fluorocarbon head group on top, as shown in the schematic. However, the bottle brush molecules may have a slanted orientation or lie down, as illustrated. These different orientations result in distinct abundances of co-emitted secondary ions, which can be detected with a lateral resolution of 10 to 15 nanometers. Another application deals with the analysis of individual extracellular vesicles, or EVs. The EVs are 50 to 100 nanometers in diameter and carry markers of the organ from which they originate, as well as the organ's disease state. To avoid misdiagnosis caused by biological heterogeneity, it is necessary to examine EVs individually. On the left are individual exosomes anchored on a substrate. When a nanoprojectile impacts the substrate, ions are ejected and sent to the mass spectrometer, where the tags attached to the biomarkers are identified. On the right, the top trace shows a mass spectrum of exosomes from a cancerous organ, while the lower trace represents the spectrum from a healthy organ. One more example concerns defects in computer chips, whose circuits are patterned via photolithography in several steps. With a drive to increase computing power, circuits are designed to be ever smaller. During this miniaturization, small residues from the lithography steps can become significant defects. Nanoprojectile secondary ion mass spectrometry enables the identification of these chemical defects in three-dimensional nanostructures. NP-SIMS with the Orion Mark II provides a unique methodology for acquiring detailed information about molecules and their environments from features as small as a few nanometers. The gold nanoparticle impact promotes the emission of intact molecular species with high lateral resolution. Ejecta from these dimensions must originate from co-localized molecules, enabling nanoscale assessment of sample homogeneity, detection of rare defects, and identification of molecular environments. NP-SIMS offers molecular vision and eliminates blind spots in surface analysis.